Hello, and welcome to this educational video developed for the meta-study, where we'll be teaching you how to review and measure intracranial saccular aneurysms. My name is David Brennan, and I'm the Senior Interventional Neuroradiology Fellow based in Beaumont Hospital, Dublin, Ireland. The aneurysm parameters we'll be asking you to record include aneurysm measurements, namely its neck, height, and diameter, and we'll go through these in the subsequent slides. And we'll also be asking you to record whether the aneurysm is thrombosed, calcified, or has an irregular appearance. All of the aneurysm measurements we'll be asking you to record will be on the same slice. The first is the aneurysm neck, shown here in green, which is defined as the space between the aneurysm sac and its underlying parent vessel. Is the height of the aneurysm, which is defined as the longest perpendicular measurement between the aneurysm neck and the dome of the sac, which is shown here in orange. The third and final measurement we'll be asking you to record is the aneurysm diameter, which is perpendicular to the aneurysm height, again on the same slice, and that is shown here in blue. Measurements, this time in more irregular aneurysms. So again, the neck is defined as the space between the aneurysm itself and its underlying vessel, shown here in green. Perpendicular to this, extending from the neck to the dome of the aneurysm sac, is the height of the aneurysm, shown here in orange. And again, the longest perpendicular measurement to this is the diameter, which is the final measurement we're asking to record, which is shown here in blue. Again, another example of an irregular aneurysm. The neck is fairly simple on this image. Perpendicular to this, extending up to the sac, is the height. And again, perpendicular to this is the diameter. So those are the three measurements we're asking to record, and they're all on the same slice. You may be tempted to manipulate the aneurysm height or diameter to get a longer measurement, but it's important that it is purely the measurement that is perpendicular to the neck and perpendicular to the height respectively. So now we're going to show you some real world examples. This is a CT angiogram that actually has three intracranial aneurysms, a left MCA aneurysm, a left anterior temporal aneurysm shown there, and here a right posterior communicating artery aneurysm. And we're going to measure each in turn. How we do this is by taking the thinnest slice available on your study. For either CT or an MRA, this will typically be a 1 mm slice, and we're going to put it into the multiplanar reformat, or the MPR function, as you can see here, which every PACS monitor has. So how are we going to measure our aneurysms? The first thing we're going to measure is the left MCA aneurysm. The first step we do after we put it into the MPR format is to center on the aneurysm using the crosshair function. Now the MCA aneurysm, or any MCA aneurysm, will generally be laterally directed, so it will best be seen on the axial plane, which is on the bottom left hand corner. Once you have centered on it, you can manipulate and rotate the crosshairs as shown here to bring the neck into its full view. How we do this is by aligning the crosshairs with the parent vessel underneath. So once you've done that, you can see the neck is fully there. And when the neck is there in its maximal view, you can do the first measurement, which is the neck as shown here. The second measurement, again, these are all on the same plane, is the height, which is perpendicular to the neck, extending from the neck to the aneurysm dome, as you can see here. And the last measurement we'll do is the aneurysm diameter, which again on the same plane is perpendicular to the height that you have just drawn. And this is shown here by this red arrow. So now we'll move on to measuring the left anterior temporal aneurysm. Again, this is the same process as before. So once you enter the multiplanar reformat, first put your crosshairs on the aneurysm, An anterior temporal aneurysm is generally inferiorly directed, so it's best examined on the coronal plane, which is on the right. So once you get your crosshairs into position over the aneurysm, then you manipulate the crosshairs in line with the parent vessel to show the neck in its best possible plane. That allows you to draw or measure the neck, as has just been shown there, and then in the same plane measure the height, which is perpendicular as we've previously shown. The final measurement you do then is perpendicular to the height, which is the diameter, which is shown here in the screen grab by that red line. And those are your 3 measurements. And now finally, we'll measure the right posterior communicating artery aneurysm. Posterior communicating artery aneurysms are generally posteriorly directed and hence will be best viewed on the sagittal plane, which is in the top left here. Again, center on the aneurysm using the crosshair function in your MPR reformat, and manipulate those crosshairs by rotating them to bring the parent vessel into view. You could see earlier that the anterior temporal aneurysm that we have just measured was quite regular. This posterior communicating artery aneurysm is quite irregular in shape, and initially it looked quite wide-necked, but by performing the manipulation and rotation of the image, you can see that it is actually quite narrow-necked, which is important because that means it's likely amenable to endovascular treatment. So once you have the crosshairs aligned with the parent vessel, you can perform your measurements. The first measurement we'll do, just like before, is our neck, which you can see being measured here. Subsequently then we will measure our height perpendicular to the neck, extending from the neck to the aneurysm dome, and lastly the diameter, which is perpendicular to the height. MRAs operate the exact same as CTAs. In this MRA you can see a young patient with a basilar tip aneurysm. Again, we will use the thinnest slice available to put this into our multiplanar reformat or MPR. Typically a 1mm slice for MRA, just as for CTA. Basilar tip aneurysms are generally superiorly directed, so superiorly or inferiorly directed aneurysms, just like the anterior temporal aneurysm we saw before, are generally best seen in the coronal plane, which you can see here on the right. So again, our first stage is to center the crosshairs on the aneurysm and zoom in. Then we will manipulate and rotate our crosshairs to bring the neck into the full view, and we do that by aligning our crosshairs or rotating our crosshairs in line with the parent vessel underneath, as you can see here. Once we have done that and we know that our neck is in the best possible view, we just move through the image or scroll through the image to get the neck in full plane, as you can see here, and now we'll start our measurements. The first again is the neck itself. Number 2 is the height perpendicular to the neck, extending all the way to the aneurysm dome, and the third again is the diameter perpendicular to the height. And that's how we will ask you to record your measurements of intracranial aneurysms. We'll also be asking you to record whether an aneurysm is thrombosed or calcified, and I will go through that now. Here is an example of a right MCA aneurysm on a non-con brain that is both thrombosed and calcified. Calcification is the easiest parameter to record. This is shown as hyperdense foci on the rim of the aneurysm that are very bright and the same density as the surrounding calvarium, as you can see here. Within the central aspect of the aneurysm, there is this heterogeneity. Firstly, there is this crescentic hyperdense or brighter rim, which the cursor is pointing there, beside the darker central portion. The darker central portion is normal blood, and the hyperdense crescentic component is actually thrombus. And how can we demonstrate that that brighter component is thrombus? Well, we can do that by looking at the corresponding CTA. So this is the corresponding CTA for the same patient, and you can see that the areas that were bright, that's hyperdense rim, that we saw in the non-con brain are actually dark here, aka they're not opacified, aka they're thrombus. And we can see that the darker areas beside them which represent normal blood, are opacified on the CTA. So the golden rule is that hyperdense thrombus on the non-con brain will not opacify on the CTA, and that calcification is on the rim or outside of the aneurysm and is the same density as bone. Sometimes you don't always need a CTA for correlation. The answer is readily apparent in the non-contrast brain, as it is in this case. So this is a multilobulated, densely calcified right MCA aneurysm, and you can even spot when we window down the heterogeneity within the center of the aneurysm. We know from the previous case that the hyperdense components or brighter components within the aneurysm represent thrombus, and the darker components beside them represent the normal filling or the opacified part of the aneurysm with blood. So this is a heavily calcified and partially thrombosed right MCA aneurysm. Over the next few slides, I'm going to show you more examples of thrombosed or calcified aneurysms. And when looking at these images, just remember the golden rule, that calcification is very hyperdense or bright foci on the rim of the aneurysm that is the same density as the surrounding skull, and that those components of an aneurysm are hyperdense on non-contrast imaging and do not opacify on a corresponding CTA. Some aneurysms can be partially thrombosed or fully thrombosed, and we're asking you to record that. Thanks for watching this educational video. Should you have any comments or questions, please do not hesitate to get in touch with us.